Hi, good evening all. So, as we are meeting for the first time, let me quickly introduce myself. Myself, Kirtan Thakkar. I am second year master student at Department of Mechanical Engineering. So, I'll be your second TA along with Abhi. I work at Cyberbotics Lab under Dr. Harid. So, my primary research area is biped locomotion, focusing towards control and optimization. So if you are at all interested, you can go over to the Cyberbotics lab and see what kind of work we are doing. It might interest you. So without wasting further time in introduction, let us just start with the recitation for the just today's recitation. So give me a moment. So okay, so here is the part that I'm going to cover today. So it is mobility analysis of real world mechanisms. So let me just start by reading the question first. So in this part, we will study the mobility of various mechanisms in real world applications. Not like in problems in the previous part, links and joints are sketched in lines and symbolic notations, which are in abstract form of real machines. So you can see it over here. Everything is just sketches and drawings. But in the real world application, you will have to examine carefully the mechanism to identify the individual links and join types. It often helps if you can visualize its motion, function, or watch video of the device. So we have provided the video for the this mechanism, which is over here. And so let us go ahead. Please determine the mobility and idle DOF of the following mechanism and compare the mobility of mechanism 3 and 4. What are the differences? Mechanism 1 is a backhoe linkage driven by three hydraulic joints. So let us start with mechanism 1 and I'll be reading the points for mechanism 2 and mechanism 3 as we go further to solve them. So first of all, I would start by writing the formula for mobility. So uh, just a minute. Yeah. So formula for mobility is in 2D is k into n minus 1 minus j plus summation of over I from 1 to j f I. So over here, this is connectivity as you must be familiar by now. Over here, number of joins, and over here, number of links. And this depends on if it is 2D, value of it will be 3. If it is 3D, value of k will be 6. So let us start with counting the number of links for the given question. Okay, so over here, so we can see there are several rings in this case. So one over here, one over here. But let's just quickly find the ground link. So you can see that so you can see that this whole part is fixed, and the link, which is this, is connected with the this part. So we can say that the link which I have just marked is a ground link. So let me highlight ground link quickly. So here it is, the ground link, and remaining links are connected with this ground link. So let us just start marking it with the numbers. So over here it is first. Uh, this one over here is second, and this one over here is third, fourth, fifth. Over here this is six. This is seven. This is eight. This is nine. This is 10. This is 11. This is okay. So we have total 12 links. You might be confused about why we have two links over here. So you can see there is a joint over here that is prismatic joint. That is basically a hydraulic cylinder, and two of the links are connected with it. Link number 2 and 3 are connected with hydraulic cylinder. That essentially is a prismatic joint. So let us write down the number of links that we have in here. So value of n is 12. Now let us quickly go over the number of joints that we have. So over here, this is first revolute joint, that is between 1 and 6. Over here, let me zoom in, otherwise it will get messy quickly. So R2 is between link 1 and 3. Then, okay, so I'll write down it on the right side. So over here it is R3, R4. Here it is R5, it is R6, R7. Then over here it is R8, R9, R10, R11. This one is P1, P2, and over here this is P3. It seems that I have missed a joint. Let me just go through it again here. So that will be R12. So you can see there are total 3 links connected at this joint. 1, 2, and these are the 3. So there will be 2 joints over here. So in total we have R12 and P is equal to 3. So value of J will be 12 plus 3 and 15. Now let us find the mobility of this question. Mobility will be, as we have discussed, value of K will be 3 in 2D case. Value of n is 12 minus 1 minus j, that is 15, plus summation of connectivity. So over here that we have 12 plus 12 into R plus 3 into P. So connectivity of R is 1, prismatic joint is 1. So in this case, our degree of freedom will be 3. And this can be seen over here as well. So we have over here, that is first hydraulic cylinder. Over here we have second hydraulic cylinder, and over here we have third hydraulic cylinder. So these are the 3 independent degree of freedom. And if you want to analyze it a little bit more, we can think it this way. So let's assume I'm gonna talk about this portion over here. I know the figure is a little messy, but just hang on for a while. So this is my link number 1. Uh, this is my link number 2, and that is one prismatic joint. Over here, link number 3, revolute joint, and over here we have our link number 6, which is the whole link. So you can see there are total 4 links, 1, 2, 3, and 6. So this is kind of a 4 bar, and that we have 1 degree of freedom in this 4 bar. And if you analyze this portion, it will be similar. If you analyze it over here, it is also similar. So we essentially have 3 4 bar over here, and with each 4 bar we have 1 degree of freedom. Okay, now next is how many idle degree of freedoms do we have. So let me first make a drawing when we do have idle degrees. So as we have discussed in the class, so we have idle degrees of freedom in the case when we have two cylindrical joints. So let me quickly make it over here. Two cylindrical joints like this. So then it will be a idle along this axis. Then if we have one cylindrical joint and one, so this is I mean this is spherical, 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 cylindrical. This is idle. Then in case if we have cylindrical and cylindrical, this is idle. And on top of that, if we have cam, then this will be idle. So in this four cases, we have idle degrees of freedom. So if you see, I guess, so if you see, there are none of the links and joint combination that resembles to this. So we can say that there are zero idle degrees of, that is DOF, and zero idle DOF. That is, yeah. Now let us move to the next part. So over here, so this is a very famous piece of instrument over here. That's, and you can see the video of this instrument over here over this link. So let us just start with highlighting number of links, number of joints in this case. So let me make one thing clear before going ahead. Uh, so this is so this joint is cylindrical joint over, oh sorry, oh my bad. So this link, this joint over here is U joint. Similarly, this joint is U joint, and over here this is cylindrical joint. So in total, we have 6 legs, and each leg has U joint, cylindrical joint, and U joint. Now, as there are, now let us analyze number of links in this case, and each leg, each leg has, so each leg is connected with the cylindrical joint. So it's kind of one link is sliding over the other link. So there will be first link and this will be second link. So each leg has 3 joints and 2 links. So first link and second link, then there will be 3, 4, 5, 6, 7, 8, 9, and 10, 11, and 12. Then the top platform is 13, ground is 14. So we can say that n is equal to 14 in this case. So as I already explained, each leg has 3 joints. So we have total 6 into 2 U joints plus 6 into 1 cylindrical joint. So we have total 18 joints in this case. So as we do not have space, we'll make some space over here and we can calculate the degrees of freedom. So as we know, formula is n minus 1 minus j plus sigma fi. I goes from 1 to j. So now we have a 3D case. So value of k will be 6. Value of n is 14 minus 1 minus value of j is 18 plus sigma. So that is connectivity. So we have 12 into u plus 6 into c. So value over here is minus 30 plus connectivity of U joint is 2. Connectivity of cylindrical joint is also 2. So that will be plus 30 and equal to 6. So mobility in this case is 6. Now let us think if we have any of ideal degrees of freedom in this case. So I will go back up and I'll check with this diagram if we have SS, SC, CC, or CAN contact. If we have either of this case, we'll have ideal degree of freedom. So in this case, we do not have any other case which resembles with this. So we have U, C, and U. So let me mark it over here. U, C, and U. So it is either CC or S and S or S and C. So there is nothing which resembles with this one. So we can say that there is no ideal ideal DOF. Now let us move towards the last question. Let me bring it. Oh, so there is a little text from the previous question, so please pardon me for that. Uh, so this is also very similar case to the last question, the same as B part, but the major difference in this case is each of the leg, it has spherical joint over here, spherical joint over here, and cylindrical joint over here. So similarly, we have 6 legs, and each leg has S, C, and S, and 6 legs. Each of them, each leg has 2 links. So let us start marking with the number of joints in this case. So over here, wow. So there will be six. So total joints will be 6 into 6. So total number of joints will be 6 into 12s, because we have 6 legs over here, and each leg has 2 spherical joint, 1 cylindrical joint, plus 6 into 6 into C. So we have total 18 joints. Oh, my bad. Now total links. So total links can be marked over here. 1, that is the platform. 2 is the ground. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So each leg has 2 links. So 12, 6, 6 into 2 plus ground link and platform. So that we have total 12 plus 1 and 1. So total we have 14 links in this case. Now let us calculate the mobility. So that will be k into n minus 1 minus j plus summation over I from 1 to j. So k is 6, n is 14, minus 1 minus 18 plus 12 into s plus 6 into C. So over here we have minus 13 plus connectivity of spherical joint is 3. Connectivity of cylindrical joint is 2. So 12 into 3 plus 6 into 2. So that is 48 minus 30. So total mobility of this system is 18. However, let's look at here. So we have for each leg, however, we have some ideal degrees of freedom. So we can see that so one leg has spherical, cylindrical, and spherical. So that is this, and so do have we have free rotation around this axis. We do have free rotation of this link too. So each link has total 2 idle DOF. So that means 6 into 2, we have total 12 idle DOF in this case. So if we have to figure out the degree of freedom in this case, then it will be mobility minus idle DOF. So that will be 18 minus 12, and that is equal to 6. So answer will be 6 for DOF in this case. However, I would want to highlight few things for this question. So if you see from the images, if you see from this image of problem number 2 and problem number 3, both of them look pretty similar apart from the combination of the joints. And purpose of both of them is also the same. Instead of U joint, we have spherical joint over here, and and over here as well, we have spherical joint instead of U joint. Regardless, apart from it, cylindrical joint is still there, which was in this case. So the purpose of this mechanism is also the same apart from the construction. And the construction gave us the mobility 18. However, 12 of them were ideal degree of freedom, which we already figured out over here. Yeah, so with this, we will end our recitation for question number 2. See you in the office hours. So remember, recitation hours are treated as office hours, so you can ask any of the doubt as you want. And we have total 4 recitation sessions: Thursday morning, Thursday evening, and 2 on Friday. So you can ask any of the doubt from the recitation or from the lecture that you have. Thank you.